So last session, we talked a lot about the process behind drawing Lewis structures. We're now going to talk about a unique shortcut to quickly draw Lewis structures. In this method, this is known as drawing Lewis structures by analogy. So the way that you go about drawing Lewis structures via analogy, first, you think of each atom in a Lewis structure as an individual ion or neutral atom with a number of valence electrons and charge. So for example, carbon we know is a group 4A element and it has 4 valence electrons. Likewise, nitrogen plus, so we have 5 electrons, but due to the +1 charge, we subtract 1. And nitrogen plus can be thought of as an atom unit containing 4 electrons. Now, what's really interesting is that when you think about drawing a Lewis structure in general, atoms and ions with the same number of valence electrons can be exchanged, can be replaced to give a new valid Lewis structure. So if you know how to draw a Lewis structure for one compound, you can substitute one of the atoms with an isoelectronic atom or ion to quickly generate a new related Lewis structure. So for example, methane looks something like this, where our carbon atom has 4 electrons to its name. Well, in terms of valence electrons. Now, if we think about ammonium, if we want to replace carbon, so we're going to replace carbon, which has 4 electrons, with nitrogen plus, which also has 4 electrons. Completing this substitution, we see that we've generated a new valid Lewis structure, which accurately represents the Lewis structure for the ammonium ion. So in effect, you can substitute and swap out interchangeably atoms and ions with the same number of valence electrons in order to generate a new unique Lewis structure. This is often a method to quickly draw Lewis structures. Let's look at another example. So ozone and sulfur dioxide. So ozone looks a little bit like this. Now, we know that oxygen has 6 electrons to its name, and we're going to try to replace oxygen with an isoelectronic atom. So we're going to replace oxygen with sulfur, which also has 6 electrons. And if you're replacing an atom with another isoelectronic atom or ion, your Lewis structure in general will be valid. So in turn, we can quickly generate a new Lewis structure for sulfur dioxide by replacing our central oxygen with sulfur. And as we can very clearly see, we've generated in a very efficient manner the structure of sulfur dioxide that we obtained from the stepwise bottom-up method. Does this idea make sense to everyone? So you can quickly generate new Lewis structures by replacing an atom with another isoelectronic atom or ion. I guess in order to be completely precise, we're technically replacing oxygen plus with 5 electrons with sulfur plus, which also has 5 electrons. Same number of electrons, atoms and ions with the same number of electrons can be exchanged in Lewis structures to generate a new valid Lewis structure. So this is a nice shortcut for taking a Lewis structure that you already know how to draw and quickly generating a new Lewis structure containing different atoms or containing a different charged ion. Does this make sense to everyone so far? Any questions so far? Okay, so let's look at just a general guiding principle. So if we wanted to think about isoelectronic atoms and ions for 4 valence electrons, we're primarily looking at our group 4A elements. The isoelectronic atoms would be any cation of a group 5A element, such as nitrogen plus or oxygen 2 plus. Likewise, 5 valence electrons, these are group 5A elements, and the isoelectronic atoms or ions would be an ion of a group 6A element or an anion of a group 4A element. So we have a wonderful way of relating the number of electrons found in different atoms and ions in our Lewis structure. And we can use this as a method to quickly generate novel or new Lewis structures from Lewis structures that we already have. Now, one thing that I want to keep in mind, drawing structures via analogy, it's a useful shortcut, but the standard method still is quite reliable and efficient. So let's demonstrate the utility of this shortcut. And we'll start by writing the Lewis structure for hydrogen cyanide from scratch. Okay, so hydrogen contributes 1 electron, carbon contributes 4 electrons, nitrogen contributes 5 electrons. That gives us 10 electrons total. Carbon is our central atom. We're going to surround it with hydrogen and nitrogen and form 1 bond each. So we have 6 electrons remaining. Now, following our rules for drawing Lewis structures, where do we place our valence electrons? Where do we place our lone pair electrons now? Where do we place our lone pair electrons? You place your lone pair electrons on the outer atom, and how many lone pair electrons does nitrogen need? How many lone pair electrons does nitrogen need? How many lone pair electrons? How many additional lone pair electrons does nitrogen need? And checking the chat, yep, that's exactly right. We need 6 lone pair electrons to complete our octet. We've used up all of our electrons. And now let's take a look at carbon. So looking at carbon, does carbon have a complete octet? Does carbon have a complete octet? No, it does not. So how many additional bonds does carbon need? How many additional bonds does carbon need? 2. Yep. So to form 2 additional bonds, we're going to take our 2 lone pairs and form a double and then a triple bond. So now that we've drawn a structure that we think follows the octet rule, let's check. So hydrogen has 2 electrons, carbon has 2 times 4 or 8 electrons, nitrogen has 3 times 2 plus 2, which is 8 electrons. So this structure follows the octet rule and is perfectly valid. Now, if we think about acetylide anion, let's think about how we would draw this structure via analogy. Well, thinking about nitrogen, nitrogen has 5 electrons, and carbon minus also has 5 electrons. So what we can do is we can take our structure for hydrogen cyanide and replace our nitrogen with carbon minus. That would generate a new valid Lewis structure for acetylide anion. So as you can see, this method of drawing structures via analogy can be quite efficient when it works. Just to show that we'd get the same answer through a parallel method, if we tried to draw this structure from scratch, Hydrogen contributes 1 electron. Carbon contributes 4 electron, and we have 2 carbons. So that gives us 9 electrons plus 1 for our -1 charge. That gives us 10 electrons total. We place our 2 carbons and 1 hydrogen. We form 1 bond each. That gives us 6 electrons to work with. We then place our 6 electrons on our outermost carbon. We don't have a complete octet, so we move 2 of our lone pairs down to form a triple bond. And that in turn gives us the following structure for acetylide anion. And one thing that I'd like you to very closely point out is that it perfectly matches the structure that we've generated via analogy. In fact, the method of structure drawing by analogy is a little bit faster because it actually already assigns the formal charges using atom motifs. If we wanted to calculate the formal charge of this carbon really quickly, we'd have 4 minus 3 plus 2, which gives us a formal charge of -1. So there are many methods to go about drawing Lewis structures. The method of analogy is just another tool that you can utilize. You can add the electrons to any element you want. It's most logical to add it to carbon, as the carbon anion is the ion that's isoelectronic with nitrogen. In general, you're looking for isoelectronic species. Does this make sense? Yep, exactly. Exactly right. Carbon anion has 5 electrons. Neutral carbon atoms have 4. And if we look at our total number of electrons, acetylide anion is isoelectronic with hydrogen cyanide. Does that make sense? Perfect. So let's take a look at the following example. Let's work on the following example, where I'd like you to draw the Lewis structures for carbon dioxide and NO2 plus. And don't be shy to type or share your answers in the chat or on this whiteboard using the annotate feature. And to allow me a method to check your work, I'd like you to tell me the number of double bonds. The number of double bonds in each of your 2 structures. So let's take a moment and let's try to draw out Lewis structures for each of the following 2 compounds, and then we'll discuss in about 5 minutes. And remember, if you have isoelectronic atoms or molecules, you can utilize the method of analogy. And we'll discuss in about 4 minutes. And the responses I see in the chat look great so far for the proposed structures. And if you have any questions, don't be shy to ask in the chat or verbally. Well, let's try to get a few more responses in the chat for the proposed structure. And the structures that I'm seeing in the chat look great so far. And we'll discuss in about 2 to 3 minutes. And if you have any questions preparing and drawing out your Lewis structure, don't be shy to ask your questions in the chat. And we'll discuss in about 1 minute. Okay, so for carbon dioxide, so let's count. Carbon contributes 4 electrons, oxygen contributes 6 electrons, and we have 2 oxygens. That gives us 12 electrons. So in total, we have 16 electrons to work with. What is our central atom? What is our central atom going to be? What is our central atom going to be for carbon dioxide? Carbon, yep. So we're going to take carbon, we're going to surround it with our 2 oxygens, and then following our step-by-step procedure, we're going to form 1 bond each. So we've used up 4 electrons, we have 12 electrons remaining. Now, where do we place our valence electron? Sorry, where do we place our lone pair electrons? On the outer or inner atoms? Where do we place our lone pair electrons? On the outer atoms or inner atoms? On the outer atoms, okay. And looking at the oxygen atoms, how many lone pair electrons do each oxygen atom need? How many lone pair electrons do we need to put on each oxygen? Yes, 2 pairs in the end, but initially for our step-by-step guide, we're going to put 3 to fulfill the octet rule. We've used up all 12 of our electrons. And now if we look at carbon, carbon doesn't have a complete octet. So how many additional bonds does carbon need? 2 more, okay? So we're going to take our 2 lone pairs and move them down to form 2 double bonds. Now you may say, why are we drawing this structure, which looks quite reasonable, versus a structure like this? Would someone like to provide a comment as to why the top structure is preferred? Why do we care about the top structure more than this bottom structure? What's the difference between these two structures? They both fulfill the octet rule, certainly, but what is different and which structure is preferred? So someone mentioned that this top structure is more stable. Okay. Let's look at the formal charges. Let's look at the formal charges. So in this top structure, the formal charge of carbon is 4 minus 4, which is 0. The formal charge of oxygen is 6 minus 4 minus 2, which is equal to 0. In this bottom structure, our formal charge of oxygen is equal to 6 minus 6 minus 1, which is negative 1. The formal charge of carbon is equal to 4 minus 4, which is 0. And the formal charge of this oxygen on the right is 6 minus 3 minus 2, which is plus 1. Now, as we can clearly see, which structure, the top or the bottom structure, minimizes formal charges? Which structure has the least amount of formal charges? Which structure has the least amount of formal charges? The top structure or the bottom structure? The top structure. Ergo, that's why this top structure is preferred, because the top structure minimizes formal charges. Okay, let's look at NO2+. Well, if we draw out our structure for carbon dioxide, we think of carbon and nitrogen plus. Both of these species have 4 electrons to their name. So I'm going to replace carbon with nitrogen plus, and that gives me the following Lewis structure via analogy. Okay, so this structure matches that of NO2+. Just to show that you'd obtain the same exact Lewis structure if you generated the structure from scratch. If we think about NO2+, nitrogen contributes 5 electrons, oxygen contributes 6 electrons, and we have 2 oxygen atoms. That gives us 17 electrons, minus 1 because we have a plus 1 charge. We place nitrogen as our central atom, and we surround it with our 2 oxygens. As we did in the previous example, just to show, we formed 1 bond each, and then we assign lone pair electrons to each atom. So we assign our 6 additional lone pair electrons to each oxygen atom, and now we're completely out of electrons. Then, just like before, we converted 2 of our lone pairs to form double bonds. Just to show that the formal charge in fact ends up on nitrogen, let's calculate the formal charge of nitrogen. So the formal charge of nitrogen is equal to nitrogen's group number of 5 minus the number of bonds, which is 4, which gives us a formal charge of plus 1. Does this make sense to everyone so far? So you can always draw your Lewis structures from scratch, but I find drawing structures by analogy can be a nice little shortcut that saves you some time. Okay, so let's keep going now, and let's talk about when you draw Lewis structures, you can often end up drawing multiple potential Lewis structures for the same formula. We'll talk about constitutional isomers and stereoisomers, which are two different types of variations found in Lewis structures with the same formula. So structures with the same formula in which the atoms are bonded in a different arrangement or connectivity are known as constitutional isomers. So for example, CH3CN has multiple plausible Lewis structures representing each constitutional isomer. So for example, CH3CN, so we have for carbon, we have 4 electrons and we have 2 of them. That gives us 8. For hydrogen, it has 1 electron and we have 3 hydrogens. That gives us 3 electrons. And nitrogen contributes 5 electrons. In total, we have 16 electrons to work with. So we're going to place our atoms surrounding our central atom of carbon. Now we can't just surround this middle carbon with hydrogens because we have 3 hydrogens. So we're going to surround our leftmost carbon with our 3 hydrogens. Note, there are many permutations for how you can arrange your atoms. We're just starting with this arrangement of atoms in order to attempt to draw our first constitutional isomer. Then we're going to form 1 bond each. We've formed a total of 5 bonds. So we've used up 10 electrons. We now have 6 electrons remaining. Now, where do we place our 6 electrons? What is our most electronegative outermost atom? What is our most electronegative outer atom? That's nitrogen. So we're going to place our 6 electrons on nitrogen. We now have 0 electrons remaining. Now, carbon, this carbon here clearly doesn't have a complete octet. So how many additional bonds do we need to carbon? How many additional bonds do we need to carbon? 2, okay? Perfect. So we'll take 2 lone pairs and convert it to 2 additional bonds. Okay. So now that we have our first valid constitutional isomer, let's go back to the initial portion when we were designing and creating the Lewis structure for this molecule. And if we change how the atoms are connected, so let's suppose for a moment that we moved our hydrogen to the nitrogen. We can generate another entirely different Lewis structure that contains the exact same atoms connected in a different arrangement. So 16 electrons, we're down to 6 electrons. Now, in this case, we place our lone pairs on our outer atoms. So we place 2 on carbon and 4 on nitrogen. We have 0 electrons remaining. And now we fulfill the octet for our central carbon by taking our lone pairs and forming additional bonds. That in turn gives us the following equally valid Lewis structure for the following compound. So as we notice, these 2 Lewis structures are known as constitutional isomers because these Lewis structures have the same formula but a different connectivity of atoms. Does that make sense? So constitutional isomers, they have the same formula, the same number of atoms of each element and the same number of electrons, but they have a different arrangement and connectivity of atoms. Any questions on this idea? Any questions on this idea? Okay, so let's talk about the next type of isomer and structures with the same formula in which the atoms are bonded with the same connectivity with a different 3D shape are known as stereoisomers. So stereoisomers have the same formula, same connectivity of atoms, but those atoms are arranged differently in 3D space. So for example, dibromoethane has both constitutional isomers and stereoisomers. So let's go through and let's just do an electron count. So for bromine, we have 7 electrons and we have 2 bromine atoms, so 14 electrons. For carbon, we have 4 electrons times 2 gives us 8. Hydrogen, 1 electron times 2, which gives us 2. That gives us 24 electrons to work with. We'll place our 2 carbon atoms as well as our bromine and hydrogen atoms surrounding our central carbon atoms. Then what we're going to do is we're going to form 1 bond each. We've used up 10 electrons, so we have 14 electrons remaining. Where do we place our lone pair electrons first? Where do we place our lone pair electrons first? Where do we place our lone pair electrons first? We place them first on bromine. So we have 2, 4, 6, 8, 10, 12. We've used up 12 electrons. We have 2 electrons remaining. Are there any atoms with an incomplete octet? Are there any atoms with an incomplete octet so far? Are there any atoms remaining with an incomplete octet that we can place our 2 electrons on? Carbon. So we'll place 2 lone pair electrons on carbon. We're now out of electrons. So for the student asking, can we place both bromines on 1 carbon? Yes, we can actually, and that would be a constitutional isomer. Exactly. We're just starting with this structure so we can start to see some variations. No, it's perfectly correct if you wanted to place both bromines on 1 atom. So now, as we notice, this right side carbon has an incomplete octet. So we're going to take our lone pair and form a double bond. So this is 1 valid structure for dibromoethane. Now we can just as easily generate a structure with both of our bromines on the same carbon. So these 2 structures are known as constitutional isomers. They have the same formula, but a different connectivity of atoms. Okay, so let's also look now. So here's our here's the Lewis structure that we drew together. Now we can draw another Lewis structure with the exact same connectivity of atoms, but that has a clearly different molecular shape. So looking at these 2 structures, let's look at the position of our bromines on our double bond. So in this top structure, the bromines are on the same side of our double bond. And thus we call our bromines, quote unquote, cis to each other. Now, if we look at this bottom structure, are our bromines on the same side of our double bond or different sides? Are they both on the top side of our double bond or are they on opposite sides? looking at our bromines in the second example, they're on opposite sides. So when we have our bromines on the opposite side of our double bond, we call our bromines, or we call this isomer, the trans isomer. So we can clearly see that our molecular shape, the shape of this molecule, is quite different depending on the relative position of our bromines in three-dimensional space. So if we look at just a crude space-filling model, we can very clearly see that if we compare our cis to our trans isomer, just looking at the crude shape of each of these molecules, is the three-dimensional shape of these molecules the same or different? Is the three-dimensional shape, how the atoms are arranged in space, the same or different? It's different. So we call these molecules where we have the same connectivity of atoms and the same formula, but a different 3D shape, we call these isomers stereoisomers. Does this make sense to everyone? Does the idea of constitutional isomers and stereoisomers make sense? So the difference between isomers and resonance is isomers has to do with the actual connectivity and bonding between atoms, while resonance is more describing a phenomena where the electrons found in bonds and lone pairs are delocalized across multiple atoms. So resonance phenomena more concern how we draw and portray the distribution of electrons, while isomers are looking at the bonding connectivity and the shape of our molecules based on that, based on how the atoms are connected together, both in terms of connectivity and in terms of shape. Does that make sense? Perfect. Okay, so let's keep going now. So let's take a look at the following example. In this case, we're asked to draw two constitutional isomers for the following compound and two stereoisomers for the following compound. So let's take about 4 to 5 minutes to work through this example, and don't be shy to message in the chat your proposed responses, or to use the annotate feature to try to draw out any of your proposed structures on our whiteboard. We'll discuss this example, and we'll discuss both of these examples in about 5 to 6 minutes. And if you have any questions, don't be shy to ask. and we'll discuss this example in about 4 to 5 minutes. And if you have any questions working through these examples, don't be shy to message me in the chat or to share your proposed structures or proposed thought process and questions in the chat. And we'll discuss this example in about 3 minutes. And if you have any questions, don't be shy to type them in the chat or unmute and ask your questions verbally. Okay, so let's discuss this example. So let's try drawing 2 constitutional isomers for the following compound. Okay, so counting carbon, we have 4 electrons and we have 2 carbons. So that gives us 8 electrons to work with. For hydrogen, we have 1 electron and we have 2, 4, 5 hydrogens. Oxygen, we have 6 electrons. Chlorine, we have 7 electrons. Okay, we're going to place our 2 carbons as the central atom, and we're going to surround them with our remaining atoms. Okay, so looking at our total electron count, 13, 20, we have 26 electrons to work with. We formed 1, 2, 3, 4, 5, 6, 7, 8 bonds. So now we have 10 electrons remaining. Now, where do we place our lone pair electrons? What atoms have an incomplete octet? What atoms have an incomplete octet? Chlorine, yep. So we're going to place 6 electrons on chlorine. Perfect. We have 4 electrons remaining. Now we look at oxygen. So we place our 4 electrons on oxygen. Okay, and now we have a complete valid Lewis structure. Now, if we wanted to think about a constitutional isomer, if we wanted to change the connectivity of our atoms, all we have to do is swap the position of 2 of our bonded atoms. So I'm just going to swap this hydrogen and chlorine atom to generate the following Lewis structure. So have I generated a constitutional isomer? Do I have a structure with the same formula, but with a different connectivity of atoms? Perfect. Okay, so let's look at this next example where we're asked to draw two stereoisomers. So for carbon, we have 4 electrons to work with, and we have 3 carbons, giving us 12 electrons total. For hydrogen, we have 5 electrons to work with. Well, let me rephrase that. 1 times 5, which gives us 5 electrons total. For chlorine, we have 7 electrons to work with. Adding this all together, we have 24 electrons to work with. Wonderful. Okay, we're going to place our 3 carbon atoms and surround each of our carbon atoms with hydrogen atoms as symmetrically as possible. We're then going to form 1 bond each, and now counting the number of electrons that we've used up, 2, 4, 6, 8, 10, 12, 14, 16. We now have 8 electrons remaining. Now what atoms have an incomplete octet? What atoms have an incomplete octet? Where do we place our 8 valence electrons? Where do we place our 8 lone pair electrons? Chlorine and carbon, okay? So for chlorine, we're going to place 6 lone pair electrons. We have 2 electrons remaining, and we'll place the remaining 2 electrons on carbon. Now, my question to all of you is, looking at this carbon, which has an incomplete octet, how many additional bonds do I need to form? One more bond. So we're going to take this lone pair on carbon and we're going to form a double bond. Okay, so currently looking at this structure, we have both of our substituents on the same side of our double bond. So we call this a cis isomer or cis stereoisomer. We can just as easily draw a stereoisomer where our substituents are found on opposite sides of the double bond. So this would be our trans stereoisomer. So the key distinction between a stereoisomer and a constitutional isomer is that a stereoisomer has the same connectivity, but a different shape. You have to change the relative position of your atom without changing the connectivity. And in this class, the majority of the stereoisomers that you see have to do with an alkene and our cis-trans stereoisomers, which are based on different relative positions of substituents about a double bond. Does this make sense? Any questions on this idea? In the first example, there are more valid answers than just the ones that I've proposed. So you can easily write a constitutional isomer that looks something like this. Yes, that would also, this would also work for a constitutional isomer. There's no reason why it can't. And that really goes to show that for the same formula, you can have a range of different possible constitutional isomers. Yes, yes, certainly. You can, so in this case, you can't just swap a chlorine for a hydrogen as the result of symmetry. But for example, this structure is a constitutional isomer of the other structures that we've drawn. We're starting to get into symmetry, which requires us to understand molecular shape and geometry. And we'll talk more about that later on in this chapter and next chapter. So the short answer is you can't quite just swap a chlorine for a hydrogen in this structure because it's symmetrical. But in most cases, the swapping atoms method will work fine. Did that answer your question? But yes, the structure that you've proposed is a valid constitutional isomer, 100%. Perfect. Okay. So let's take a moment now, and I'm going to start us off. Let's try to draw the Lewis structure for the following ions. And this will really be a lead-in to our next discussion. So for carbonate, so carbon contributes 4 electrons, oxygen contributes 6 electrons. Okay. We have 3 oxygen atoms. That gives us 22 electrons to work with, plus 2 for our -2 charge. That gives us 24 electrons. We put carbon as our central atom, and we surround it with 3 oxygen atoms. Then we form 1 bond each. Okay. That in turn gives us 18 electrons remaining. Where do we place our lone pair electrons? Where do we place our lone pair electrons? What are our outermost atoms?
Oxygen?
Yep. So we'll place 6 electrons on each oxygen atom. Okay, we've used up all of our electrons. And now for carbon, in order to fulfill its octet, how many additional bonds does carbon need? 1. Okay, so let's take one of our lone pairs and form a double bond. Note, it doesn't actually matter which lone pair we choose. They're all identical. Now let's calculate the formal charges. So the formal charge for oxygen number 1, so the oxygen on top, is equal to 6 minus 2 plus 4, which gives us 0. Let's look at the formal charge of the oxygen on the bottom. This is a charged molecule, so you need to make sure that your formal charges of all of your atoms add up to your total charge. So the formal charge of this bottom oxygen, would someone like to type that in the chat? What is the formal charge of this bottom oxygen right here? And the calculation I see in the chat, remember you add up the number of lone pair electrons and the number of bonds. So what would the formal charge be for this bottom oxygen? This is a really important skill to check your work. The formal charge, so we have our group number, which is 6, minus the number of bonds, which is 1, plus the number of lone pair electrons. And that gives us a formal charge of -1 for each of these bottom oxygen atoms. Finally, the formal charge of carbon is equal to 4 minus 4, which gives us a formal charge of 0. As we can see, if we add up our formal charges, our total formal charge on all of our atoms is equal to -1 minus 1, which is equal to -2. That matches our overall charge of 2 minus. Does that make sense? Any questions on this example? Any questions on this example? Okay, so let's now take a moment and let's try to draw the Lewis structure for NO3 minus. You can draw this using the from scratch method, or you can try drawing it via analogy if you're being creative. And I'd like you to type in the chat the total number of bonds and the formal charge of each atom. So let's spend about 4 to 5 minutes drawing out these Lewis structures, and then we'll discuss this example momentarily. And we'll discuss this example in about 4 minutes. And we'll discuss this example in about 2 to 3 minutes. And let's try to get a few responses in the chat or any questions in the chat, just to make sure everyone's comfortable going through the process of drawing Lewis structures. And the responses I see in the chat look great so far. And the formal charge assignments that I'm seeing in the chat look great so far. And we'll discuss this example in about 1.5 to 2 minutes. Okay, so let's discuss this example. So I'm going to very conspicuously draw out our previous structure for carbonate. Okay, now why am I drawing the structure for carbonate, you may ask? Well, if we think about it, so CO3 2-, we can replace carbon, which has 4 electrons, with nitrogen plus, which also has 4 electrons. And that would give us the structure for nitrate that looks something like this. With our total charge being -1. So if you're quick at drawing structures via analogy, you can very quickly generate the desired Lewis structure. Let's do this from scratch because the analogy method, although it's nice, it's usable, it works well, but it's not as common as the other methods. So let's count up our electrons. So we have 23 plus 1, or 24 electrons. Now what we're going to do is we're going to place nitrogen as our central atom. We're going to form 1 bond each to each of our oxygen atoms. That gives us 18 electrons. Just like before, we place our 18 electrons on each of our surrounding oxygens. And then, in order to complete the octet on nitrogen, we convert a lone pair to a double bond. It does not matter which lone pair you convert. The formal charges for these 2 oxygens are -1. We can show that by taking 6 minus 6 plus 1, which is -1. The formal charge of our nitrogen atom is equal to 5 minus 4, which is +1. And the formal charge of our second oxygen right here, let's calculate that. The formal charge of our oxygen number 2 is equal to 6 minus 4 minus 2, which gives us a formal charge of 0. If we add up our formal charges in total, we have -1 minus 1 plus 1, which gives us a formal charge, which gives us a total charge of -1. Does this example make sense to everyone so far? So, what do I want you to take away from this? Why am I having you do this example? Well, it's great for testing your ability to draw Lewis structures. That's one thing, but let's touch on a key point. Remember how I mentioned that it doesn't matter where you form your double bond? Let's look a little bit at these systems such as carbonate and nitrate and begin to understand how our Lewis structures compare to the actual distribution of electrons in these molecules. Okay, so what we're going to do is we're going to talk a little bit about resonance. So what is resonance? Well, let's start by defining a resonance structure. A resonance structure is one or more valid Lewis structures with the same skeletal formula, bond connectivity, but a different distribution of electrons in bonds and lone pairs. So we call a pi bond a double or a triple bond, and adjacent pi bonds overlap to form a pi system. Further, if a lone pair is adjacent to a pi bond, the lone pair is spread or delocalized across the pi system. Another way of thinking about resonance is that electrons shared between atoms in double and triple bonds and electron pairs on atoms adjacent to double and triple bonds are delocalized across all atoms in the pi system. So for example, let's suppose that I have two adjacent double bonds. Okay, so these two adjacent double bonds form what's known as a pi system. So a pi system consists of pi bonds, which are double and triple bonds. And essentially what's occurring in our pi system is that rather than our electrons being localized on a single atom, instead, in resonance, we have our 4 electrons in our pi bonds, in our double bonds, delocalized or spread across multiple atoms. So electron density in our double bonds are spread over all quote unquote conjugated atoms. So all atoms that are in connected adjacent pi systems, connected or adjacent double bonds. So when we draw resonance structures, our goal is to as accurately as possible depict the many different ways we can distribute our electron density in the form of bonds and lone pairs, and in turn get a sense of how, on average, where are our electrons located and how are our electrons distributed in our molecule. Does that idea make sense? So fundamentally, resonance, if I had to boil it down, is the electron density found in adjacent pi bonds is spread over multiple atoms. It's delocalized, it's spread out over all of the atoms conjugated and participating in resonance. Can I get some responses in the chat just to see if everyone's comfortable with this idea? That electrons are spread over multiple conjugated atoms participating in resonance. Any questions? Okay, so let's see how this works in practice. So we can draw multiple Lewis structures showing different distributions of electrons that obey the octet rule for a molecule. So resonance structures are not different molecules. They're the same molecule, and we're just taking snapshots of different ways that we can arrange the electron density. This is just our way of thinking about the electron density in a molecule. None of the resonance structures are accurately representative of the true distribution of electron density. And we'll talk about how to correlate these resonance structures, which are our way of drawing and depicting ways that we can distribute our electron density versus the actual distribution of electron density in our molecule, which is best thought of as an average of resonance structures. More on that later. So let's start for carbonate. So for carbonate, we had a discussion where we had our double bond formed with the top oxygen. Now I'm going to put, and I'm going to color in a different color, some of our lone pairs adjacent to our double bond. So we call our double bond, that's our pi bond, and lone pairs adjacent to our pi bond are considered quote unquote conjugated lone pairs. And what that means is this lone pair can participate in resonance and can be spread across multiple atoms through this pi bond. Okay, so let's pretend for a moment that we want to change how our electron density is distributed, or how we draw our electron density. So to do this, we're going to use what's known as the arrow pushing shortcut. If you have a lone pair adjacent to a pi bond, you can push the lone pair down to form a new pi bond. As you form a new bond, the previous pi bond breaks and we get a new lone pair. This is known as arrow pushing notation. And if you're taking organic, this is the backbone of drawing reaction mechanisms. So quite simply, you take your conjugated lone pair, you form a double bond with it, and you take your double bond and you put the lone pair back on the atom. Okay, so we've done a pretty good job so far. And my question to all of you is there another place that we can put our double bond? So we covered the top, we covered the right, and can we just as easily form a double bond with the left oxygen atom? Can we just as easily use arrow pushing notation to form a double bond with the oxygen on the left? Yeah, we can. So we kick our lone pair down, our double bond gets kicked up, and that in turn gives us the following resonance structure. Now we denote resonance structures using these double-headed arrows. And it's really important that you follow that convention. Now, again, I always want to preface this with this idea that these resonance structures are just pictures. These resonance structures are just our way of thinking about how electrons are distributed in our molecule. We can even go one step further and think about formal charges. And we can say, oh, in some of our resonance structures, our negative formal charge is found on some atoms. In other resonance structures, our negative formal charge is found on different oxygen atoms. Now, this is important because as we can very clearly see in each of these resonance structure snapshots, the electron density and our negative charge on each of our oxygen atoms has been spread or delocalized across all of our atoms participating in resonance. Does everyone see how in each of our snapshots, if we look at them holistically, if we look at them overall, this negative formal charge has been spread over multiple atoms? Does everyone see how this negative formal charge, how our electron density is spread over multiple atoms? Does everyone see how in each of the, if we look at these snapshots as a whole, our negative formal charge has ended up on all of our oxygen atoms, looking at all of these snapshots? And that really gets at the core of resonance. It's this idea that electrons are spread out across all atoms participating in resonance. And we can draw snapshots of how electron density can be distributed using arrow pushing notation. In reality, our actual structure is an average. So in reality, rather than drawing formal single and double bonds, and rather than drawing full charges, in reality, you can best think of the true structure as if we're spreading our electron density across multiple atoms, and we are spreading our negative charge across multiple atoms. We'll talk more about how to draw the best depiction of the actual structure momentarily. Now, just a side note, resonance is not rotation. So to showcase this, let's pretend if we were, for some reason, we had like radio labeling and we had a specific isotope that we could detect for oxygen. So let's make that very clear that this oxygen is in fact different. Resonance is not rotation. It's not like we're just rotating this carbonate ion. We are actually changing, and we're drawing different depictions of how our electron density is arranged in our molecule. Now, the reason why we care so much about resonance structures is that they provide us an enormous amount of insight into patterns associated with reactivity and patterns associated with charge distribution. So again, resonance is not rotation. We are drawing different pictures for how we can distribute electron density in our molecule. Now, resonance structures fundamentally are drawing and visualizing different distributions of electron density. The molecule doesn't actually adopt the structure of any one resonance structure. Rather, the actual distribution of electron density is the weighted average of all resonance structures based on their stability assessed using formal charge rules. And when I use stability, I don't mean in like the thermodynamic sense. It's more this idea that we have these rules for assessing what makes a good, low energy, reasonable Lewis structure. And what we do is we look at all of our resonance structures, weight them based on their validity as a Lewis structure. And from this weighted average, we can put together an idea of how the electrons are actually distributed in our molecule. Okay, so where this comes up and where we see this weighted average, so in terms of bond length, strength, is where we start to think about bond order. So bond order is the number of bonds between two atoms. Okay, wonderful. Why is that important? Well, if we look at carbonate, we were able to draw the following three resonance structures. So this is just a recap. So for carbonate, we are able to draw the following three resonance structures. Again, we use these double-headed arrows to showcase the fact that we are in fact dealing with resonance structures. Okay, one more. Okay, so we have each of our structures. Now, in terms of our weighted average, if we wanted to calculate the average bond order, what we do is we take the bond order in each structure, and then we divide it by the number of resonance structures. So let's look at an example. So let's look at this top carbon-oxygen bond. So if we wanted to calculate the average bond order, if we wanted to calculate the bond order that we would see in our resonance structure, what is the bond order in our first resonance structure? How many bonds are formed between carbon and oxygen? How many bonds are formed between carbon and oxygen in our first structure? How many lines do we see? Just between the top carbon and oxygen. How many bonds are formed between the top carbon and oxygen? We have 2 in our first structure. What about in our second structure? What is the bond order for this top carbon-oxygen bond in our second resonance structure? 1, okay. In our third structure, what is our bond order? 1, okay. So we add up our bond order in each structure. We're looking at this top carbon-oxygen bond, and now we divide by our total number of resonance structures, which is 3. And that gives us a bond order of 4/3, which is equal to 1 1/3. Okay? So what this is telling us is we don't quite have a genuine double bond. Instead, we have a bond that is stronger than a single bond, but weaker than a double bond, because we're spreading out our electron density across multiple atoms. So we can also look at our average formal charge. So we can calculate our average formal charge. In this case, we take the formal charge of each of our atoms in each of our structures and divide it by the total number of resonance structures. So in our first structure, what is the formal charge on this bottom left oxygen? What's the formal charge? -1, yep. Okay, what about in our second resonance structure? What's the formal charge of this? Just reading off the formal charge that we've calculated, and yes, that equation is correct, and the formal charge for this bottom left oxygen in our middle resonance structure is also -1. What about in our far right resonance structure? Sorry about that. In our far right resonance structure, what is the formal charge on this oxygen? What is the formal charge on this oxygen? What is the formal charge on this oxygen right here in the far right resonance structure as drawn currently? Is it -1 or is it 0? Looking at this oxygen in this specific resonance structure, it's 0. We then divide by our total number of structures, and that gives us -2/3. So again, we don't have a full -1 charge. Instead, we have a -2/3 formal charge on each of our oxygen atoms. So if we were to draw an accurate depiction of our average structure or our true structure, so on average, we would have not quite double bonds, but a 1 1/3 bond. And on average, each of our oxygen atoms would have a formal charge of approximately -2/3. So this average depiction, or our resonance hybrid, is our best way of depicting the average bond length, strength, and formal charge found about all of our resonance structures. So the true structure would more closely resemble this average structure, otherwise known as the resonance hybrid. Does this idea of the average structure make sense to everyone? Does this idea of the average structure make sense? Any questions on this idea? Yes, if you looked at the oxygen atom in carbonate, you'd more likely see a charge that most resembles negative 2/3. Yep. And that's because each of these Lewis structures that we draw are just snapshots. They're potential ways that we can distribute our electron density. Our actual structure is more of an average of all of our resonance structures weighted by stability. So what I want us to do now is I'd like us to take a moment and I'd like us to try and draw all the reasonable resonance structures for nitrate. So make sure you're still following the octet rule and formal charge rules. And I'd like you to answer the question, what is the bond order for the nitrogen-oxygen bond? Yes, this is very common in organic chemistry. So what we're going to do now is we're going to work on the following example, and I'd like you to tell me in the chat after you're done drawing your resonance structures, what is the average bond order for the nitrogen-oxygen bond? And if you have any questions working through this example, we'll discuss in about 3 to 4 minutes. Yes, that formal charge expression looks great. That's perfectly correct. And we'll discuss this example in about another 3 minutes. If you have two lone pair electrons, you'd plug in a 2 for your total number of lone pair electrons. Unless you're saying in the chat that you have 2 lone pairs. Are you referring to lone pair electrons or lone pairs in your calculation? For if you had two pairs of electrons, then you have 4 electrons total. That's correct. And we'll discuss this example in about 2 to 3 minutes. I'd like to see some responses in the chat for the average bond order for the nitrogen-oxygen bond, just so that way I can check to see that everyone's comfortable with the material. And does anyone have a proposed response for the average? Make sure, so in your equation, when you're calculating formal charge, you add the number of bonds to the number of lone pair electrons. That may be why for your calculation, you're getting an odd number when you plug in your number of electrons and the number of bonds into your equation. Yep, perfect. Let's try to get some responses in the chat for our average bond order. And the responses I'm seeing in the chat look great so far, and we'll discuss in about 1 minute. The average bond order is the bond order in each resonance structure averaged and over each total number of resonance structures. So bond order is based on the number of bonds between a given set of atoms in each of your resonance structures, averaged by the number of resonance structures you have. Yes, exactly right. We have a total of 3 plausible and majorly contributing resonance structures. Okay, so let's discuss this example. So for nitrate, we've previously generated the following Lewis structure. Now what we're going to do, and I'm going to color code these electrons. We have a set of conjugated lone pairs, which are lone pairs that are adjacent to a double bond. So we can push those lone pairs down and generate a new resonance structure. Let me draw the other arrow for completeness. Remember, your structures still have to follow the octet rule. So you can't break the octet rule when you're drawing resonance structures. And we still have to consider formal charges. So our double bond on top gets broken. We form a double bond with our bottom oxygen. Likewise, we can draw another resonance structure. Okay, adding in our formal charges. So just to show that calculation, the formal charge for oxygen would be our group number 6 minus our number of bonds plus the number of electrons, which gives us a formal charge of -1. The formal charge of nitrogen, as we've actually already calculated for nitrate, would be 5 minus 4, which would be +1. Okay, so now let's look at bond order. So let's look at our average bond order. And you have to be specific here. What nitrogen-oxygen bond are you referring to? In this case, I worded this question in a very clever way because all the nitrogen-oxygen bonds are in fact identical in this structure due to the fact that the electron density found in our double bonds is delocalized across all of our nitrogen-oxygen bonds. Nonetheless, let's look at our bottom left bond and let's look, what is our bond order in each of our 3 resonance structures? So in our first leftmost structure, what is the bond order on our leftmost oxygen? What is our bond order on the leftmost oxygen? One, exactly right. Okay, so we have a bond order of 1. What is the bond order in the second resonance structure? 1, okay. What is the bond order for this bottom left oxygen in our third resonance structure? 2, okay. And how many total resonance structures have we drawn? How many resonance structures have we drawn? 3, exactly right. That in turn gives us an average bond order of 1 1/3. So to help everyone see what this average would look like, we'd have our nitrogen and we'd have our 3 oxygens. We definitely have 1 bond each. And then rather than a single or double bond, it would be a 1 1/3 bond. This bond is stronger than a single bond. How'd I get 2? How many bonds do we have in this rightmost structure? How many bonds do we see? 2. That's where the 2 came from. Does that make sense? Perfect, perfect. So in our resonance hybrid, so this is our average structure, and this is our best representative of our actual structure. We have 1 1/3 bonds, and the average formal charge would be roughly -2/3 on each of our oxygen atoms, while nitrogen has a positive formal charge. Yes, if you're adding up the charges, that will give you the average formal charge, which is also important. So if you got -2/3 for your average formal charge, that's perfectly correct. And the key point I want to make, and this is the key payoff of resonance, by drawing these resonance structures, these pictures for how electrons can be distributed in our molecule, and taking a holistic average of all of our resonance structures, we can begin to describe and get a sense of how is our electron density actually distributed in our molecule, what sites have excess electron density, what sites do not have electron density, and from that information, we can begin to understand reactivity. Okay. Any questions? You don't need to have brackets for the hybrid, but because it's charged, we would probably put the whole structure in brackets and put a minus. The bracket is only necessary when you're talking about multiple distinct resonance structures. But because this is a charged species, we would need to put it in brackets. That is correct. Okay, so as our last example before we finish off this session, actually what we'll do is we'll start off our laboratory lecture with this next example because it's somewhat lengthy and it's a great sort of exam-like question for us to practice. So what we're going to do is we're going to pause this recording